Hello and welcome to our last lecture in the series. Today I want to develop further the method of separation of variables and apply it to problems with several dimensions. We already saw how the method works in the case of the two-dimensional Laplace equation. What I'd like to discuss now is the solution of the Laplace equation in a circular domain. You might be wondering what would change, since the Laplace equation should be independent of the domain. Well, this is only partially accurate. If we keep the coordinates to be x and y, then the Laplace equation doesn't change. However, if we work on a circular domain, it makes sense to switch to polar coordinates. And unfortunately, changing to polar coordinates changes the way we take derivatives. So the equation changes its form. In a circular domain, the Laplace equation has a different form. It's urr plus 1 over r u sub r plus 1 over r squared u theta theta. And that should be equal to 0. The reason the equation looks so different is because the coordinates are no longer just the perpendicular coordinates, like the coordinates with x and y. If you're wondering how to derive this equation, there are many derivations available online, and I encourage you to look at them. The Laplace equation needs boundary conditions, and since the boundary is just a circular boundary around the disk, there's only one boundary condition. Is if the disk is of radius m, then at the radius m for any angle theta, u should be equal to some function of theta. Since we're working in a circular domain, we do expect that the function u and the function f of theta are both 2π periodic with respect to variable theta. This expectation will help us to select the right kind of solutions from the method of separation of variables. So just like in the case of the x and y and t coordinates, we expect, or we assume, that the solution u of r theta is the summation of building block solutions. Usually we have a constant in front of it, but we're going to see that the constants will be included into one part of the solutions. We expect each building block solution to be a product of two functions, one that depends only on r and one that depends only on theta. We also assume that each solution u sub n satisfies the Laplacian equation. And if we plug it into the Laplacian equation, we get that r double prime times theta plus 1 over r prime times theta plus 1 over r squared r times theta double prime should be 0. Splitting the variables, we get the following fractions. Get that r double prime plus 1 over r prime divided by 1 over r squared r should be equal minus theta double prime over theta. And by looking at this fraction, we'll make a conclusion that these fractions have to be constant. This time we're going to make them equal to some positive sigma. Later on you'll see why I'm making this choice. We looked at theta first. The differential equation for theta reads theta double prime plus sigma theta should be 0. We also expect theta to be 2π periodic. The three possible situations for constant sigma. The first is usually when sigma is equal to 0. This leads to theta double prime to be 0, which means that theta of theta is just a linear function. Since theta of theta has to be 2π periodic, this leads to the necessity of the constant alpha 1 to be 0, and alpha naught is any constant. Thus, u sub 0 of r theta is just some kind of a constant times r of r. Second possibility is when sigma is negative. Let's just say sigma is minus lambda squared. This leads to the equation theta double prime minus lambda squared theta should be equal to 0, giving us the solution that theta of theta is alpha 1 times e to the minus lambda theta plus alpha 2 times e to the positive lambda theta. The periodicity leads to the conclusion that both alpha 1 and alpha 2 have to be 0. There is no way that these two exponential functions will make anything 2 pi periodic unless alpha 1 and alpha 2 are 0. The last probability is when sigma is positive. Say sigma is positive lambda squared. The equation reads theta double prime plus lambda squared theta equals 0. We already know that the solutions have to be sines and cosines. Theta being 2 pi periodic leads to lambda being a positive integer. This is the only way to make the cosine of lambda theta and sine of lambda theta to be 2 pi periodic with respect to theta. Therefore, theta of theta is alpha 1 cosine of n theta plus alpha 2 sine of n theta. And sigma is n squared. Having figured out sigma, we can figure out what r of r is. We have the equation for r of r that r squared r double prime plus r times r prime minus n squared times r of r has to be 0. You probably have not seen equations like that in your differential equation class. So how do we get a solution? Well, there is one observation that you can see, that r double prime is multiplied by r squared, r prime is multiplied by r, and r itself is multiplied by the constant. So it seems like when we take a derivative of capital R, we lose 1 power of r. When we take two derivatives capital R, we lose 2 powers of r. And there's only one type of functions that does something like that. Those are the polynomials. The polynomials, when you take a derivative, they take a hit at the power. So the idea here is to look for the solutions of r to some power. And if you plug in r to the power m, you get the following equation, that r squared times m minus 1 times r to the power m minus 2 plus r times m times r to the power m minus 1 minus n squared times r to the power m should be 0. Very quickly you realize that this is only possible if m squared minus n squared equals 0. Therefore, r of r must be some constant times r to the power n plus the other constant times r to the power minus n. We can quickly see that we can rule out r to the power minus n, because otherwise at 0 this is going to go to infinity. Therefore, it must be that it's just a constant times r to the power n, and here we can assume that c1 is 1. Thus, making the building block solutions being r to the power n times alpha 1 times cosine of n theta plus alpha 2 times sine of n theta. We can join it with the solution that we obtained for the case when sigma was 0 and just say that u of r theta is going to be some constant, which I'm going to call a naught, plus the sum as n goes from 1 to infinity, r to the power n times, I'm just going to call the alpha 1 an times cosine of n theta plus alpha 2, I'm going to call it bn times sine of n theta. And at this point we can recognize that this is a real Fourier series for the boundary condition f of theta. So given that u of m theta was just function f of theta, we plug in m into r, and using the formulas we had for the Fourier series, we can derive that a naught is simply the integral from 0 to 2 pi times 1 over 2 pi of f of theta d theta. An is the integral 2 over L, and L here is 2 pi, so it's going to be 2 over 2 pi, but we also need to divide by m to the power n times the integral from 0 to 2 pi f of theta times cosine of n theta d theta. And Bn will be 2 over 2 pi times 1 over m to the power n times the integral of f of theta times sine of n theta d theta. These formulas are just the formulas for the coefficients for the real Fourier series. Let's consider a simple example. Suppose we have a disk of radius 3 and we have the Laplace equation satisfied over that disk, and the boundary is given as sine of theta times this function, which basically says that sine of theta only applies for theta being from 0 to pi. So if I'd like to visualize this disk, then from angle going from 0 to pi, this is sine theta, which just increases to pi over 2 and then decreases down. And then for the rest of the border, it's 0. So this is the boundary. And what the membrane should do is occupy the position of least potential energy. That's the physical interpretation of the Laplace equation here. So U of r theta will be the sum of A naught, and the sum as n goes from 1 to infinity of an times r to the power n times cosine of n theta plus bn r to the power n times sine of n theta, where a naught is going to be the integral 1 over 2 pi in front of it, from 0 to 2 pi of sine theta times h of theta minus h of theta minus pi d theta, which is the same as the integral from 0 to pi, so it's 1 over 2 pi, the integral from 0 to pi of sine theta. The coefficient an is going to be 2 over 2 pi, so it's 1 over pi, times 1 over 3 to the power n, times the integral from 0 to pi, because that's the only region where the boundary condition is non-zero, and the Bn is computed according to our formula. This is the function that's been given to me. When we evaluate these integrals, we'll see that this integral will have a problem when n equals 1. So I'm going to evaluate an and bn as n converges to 1. The other values can be ignored because this is for the other function that I want to demonstrate as well. Then we're going to add everything up. When n is 1, I'm going to use the limit that I computed. N is 3 and n is 5 just as well. Otherwise, I'm going to use the function an multiplied with cosine. Then I'm going to plot the solution. The x-coordinate will be computed as r cosine theta, y-coordinate is going to be computed as r sine theta, and the z-coordinate is going to be computed as the summation. And this is the result. This line here is the boundary, theta equals 0. There's really no significance to that line, but we can see that the shape is taking just what I predicted. It bulges upwards a little bit in the middle just because that's its position. That would be the position of the least potential energy. I can exaggerate the effect by multiplying the boundary by 5. Naturally, it increases my limits. I can reevaluate the sum and redraw the function, and you can see how things are taking shape. This is a much more pronounced effect of this boundary. I also wanted to look at what's going to happen if I take the boundary that's just some random combination of sines and cosines. This is where you can see why I want to evaluate the limits and it goes to 3 and then goes to 5, because this is where these formulas have problems. Recomputing the limits, recomputing the sum, and this is what happens. The boundary is a bit wild, but you can think about if this is some sort of a stretchy fabric that I made to assume this kind of a position, and this probably would be the shape that it's going to take. Alright, so what we have seen is that in polar coordinates, the solution with the method of separation variables produces completely different functions, because in polar coordinates everything is different. The equation is different and the solutions are different. Despite the fact that this equation represents the same process, this should be expected because functions expressed in Cartesian coordinates x and y and the same functions expressed with polar coordinates r theta will have a completely different expressions. So let's switch to two-dimensional heat equation and two-dimensional wave equation. The only change that's going to appear in that equation is going to be on the Laplacian side. For the heat equation, we had that the ut was equal some constant kappa, which is the heat conductivity constant, times uxx, but this time we're going to have uxx plus uyy. The derivation of this is quite interesting. The derivation of this equation will require some advanced multivariable integration, so I'm going to skip it from here. Now, since we have two variables x and y, the boundary is going to be since now we're talking about objects in two dimensions, the boundary is going to be not just 2 points at two ends of a string or two ends of a rod, it's going to be a two-dimensional curve. So we're going to consider only the rectangular plate, and we're only going to consider the problem where the function is 0 at the boundary. Because even in the case of non-zero boundaries, we're going to reduce the problem we're solving to a zero boundary problem anyway. So we're going to assume that when the x 0 and y equals 0 would be equal to u. Let's say y goes from 0 to b would be equal to u when x is 0 and y is anything, and it's going to be the same as u when, say, x equals a, and it's all going to be 0. So here we assume that x belongs to the interval from 0 to a, and y belongs to the interval from 0 to b. We also need initial conditions. So u of x, y at time t equals 0 will be some kind of function that depends on x and y. So initially our plate will have some heat distribution, and then the conduction of heat processes will take place, and we'll observe the evolution of the heat distribution of this plate. Just as before, we're going to assume that the solution is a summation of building block solutions. And just as before, we can assume that each building block solution is a product, this time of 3 functions that depend on their respective variables. Plugging this into the equation, then when we take derivative, we get x times y times t prime, and that should be equal constant kappa times x double prime times y times t plus x times y double prime times t. Dividing by kappa, dividing by x and y and t, we get that t prime over kappa t equals x double prime over x plus y double prime over y. First, let's try to extract x of x from this equation. We can rewrite it as t prime over kappa t minus y double prime over y should be equal x double prime over x. And just as before, we arrived at the conclusion that these two sides of the equation must be constant, because on one side of the equation depends on t and y, and another side depends on x. That's only possible, and both of them are constant. This gives us the equation for x, that x double prime plus sigma x equals 0. And given that the boundary is always at 0 on all four sides of the rectangle, we're going to require that x of 0 should be the same as x of a, and that should be 0. We know that the only possible solutions that we can get from here are x of x equals sine of pi n x over a, and the constant sigma being pi n over a squared. After we figure out x, let's figure out y. We have an equation that t prime over kappa t minus y double prime over y should be minus sigma. We can rewrite this equation as t prime over kappa t plus sigma should be equal y double prime over y. And again, on both sides of the equation, we have different variables. The left side depends only on t, the right side depends only on y. This must be yet another constant. I'm going to denote it as minus eta. Eta is yet another Greek variable. There's a tradition of using Greek variables for this kind of things, and I'm going to stick to that tradition. This gives us an equation for y. Y double prime plus eta y should be 0. And again, since all sides of this rectangle are clamped at 0, the boundary conditions for y also must be 0. And now the solution to this problem is going to be y of y equals sine. And in this case, let me just introduce another integer here. So it's going to be sine of pi m y over b. Why should I use a different integer? Because eta is a constant that's completely independent of sigma. And if sigma is indexed with n, eta doesn't have to coordinate with sigma to have the same n inside of it. The solution to this problem will work for whatever m, and it has to be independent of n that I chose for x. Therefore, eta must be pi m over b squared. Now I can use this information to solve for t. Know that t prime over kt plus sigma is equal to minus theta. That's the last form of this equation. Well, this gives us that t prime plus k times sigma plus eta times t should be 0. We don't have any initial conditions on t, so the solution is going to be some kind of a constant. Since we have a different solution for every m and every n, this constant has to be different for every n and m. Times e to the minus kappa. Inside I have sigma plus theta, and sigma is pi n over a squared, and eta is pi m over b squared, all that multiplied by t. So basically, this makes the overall solution u being equal to sum as n goes from 1 to infinity and m goes from 1 to infinity. And this runs a little bit contrary to the prediction that I made, that our solution is a sum in terms of n only. So here, this assumption was a bit incorrect. We now have a double index. But we still have a number of solutions, that we're going to add up. So this wasn't that bad of an assumption. We have Cmn times e to the minus kappa pi n over a squared pi m over b squared times sine of pi n x over a times, move it a little bit down, times sine of pi m y over b. So now the big question is, how do we determine the constant Cmn? Well, that has to be determined from the initial condition. We know that f of xy equals u of x, y, 0, and that's the double summation of Cmn. So here I'm saying m and n both start at 1 and they go to infinity, each in their own, with their own pace, times exponential term turns into 1 when t is 0. I forgot to put t right here. Times sine of pi n x over a times sine of pi m y over b. So, what if I want to figure out the constant Cmn where m is, say, 3 and n is 5? Well, I should multiply by sine of 3 pi y over b, and then when I integrate, it will get rid of all the other signs with y except for m equals 3. And then I should multiply by sine of 5 pi x over a to get rid of all of the things when n is not 5, in our coefficient of c with m equals 3 and n equals 5. So basically I will have to do a double dot product to single out C35. To cut down on the lengthy explanation, I'm just going to write the formula. That if I want the constant Cmn, 2 over the length of the interval for the x dot product, which was a, times 2 over the length of the integral for the y dot product, which was b, multiplied by an integral. In terms of x, it will go from 0 to a, and in terms of y, it would go from 0 to b, and I would have to take f of xy and multiply it by sine of pi n x over a and sine of pi m y over b, and integrate first with respect to y and then with respect to x. So this is moderately more complicated, but you can see that it's exactly the same ideas implemented just for 3 dimensions now. It's interesting to see how method of separation of variables played out for several variables, x and y. So here first we separated x, and we introduced a single constant for x in this equation. Then we singled out y and assigned a constant to y. And then when we start solving for t, we assembled the constant together. You can easily see if we had a z in this equation, then first we would single out x and leave y and z together with t. On the next step, we'll single out y, leaving t and z together. And then the next step, we'll single out z, leaving t with all the constants. And then when we solve for t, we'll just assemble 3 constants, and we get the equation for t that will have all 3 constants in them. So it's hard to expand this to 3 dimensions. Then our building block solutions are now comprised of a product of sines of x and sines of y and exponentials in terms of t. And that requires a different kind of a dot product, different kind of a projection to figure out every coefficient. So now we have to do double integrals because it's the sine series in both x and y, and we do one dot product with y to figure out the y part of this coefficient, and we also need to do the dot product with x to figure out the x part of this coefficient. So again, let's look at a simple problem. We have ut equals Laplacian in terms of x and y of uxyt, which means it's uxx plus uyy. The constant kappa here is 1, so it's something that's going to simplify our solution here. I have 0 boundary condition, and I know that x and y go from 0 to 3, and this is kind of an interesting function that I have here. So it's 1 on the region with x minus 1 and y minus 1, both in absolute values, add up to something less or equal to 1, otherwise the initial condition is 0. Well, this looks very, very complicated, but you'll see that in Mathematica it's actually quite a simple initial condition. So I said it's going to be a function that's going to be 1 when this condition is satisfied and 0 for all other x and y. If we plot it, it's just a function that has a step to 1 on this little square that kind of turned sideways a little bit, that leaves on the interval from 0 to 2 for both x and y. So Cmn is going to be 2 over 3 times 2 over 3, integrate f of xy times sine of pi n x over 3 and sine of pi my over 3, integrate in terms of x, in terms of y. And just so that the integration doesn't get too confused, I'm telling my integration that both m and n are integers. This is the result of integration. You can also see that when m equals to n, I'm going to have a 0 in the denominator. So I'm going to specifically compute a limit what happens with m equals n. Then I'm going to compute the sum. So I'm going to use the coefficient Cmn whenever m is not the same as n. When m is the same as n, I'm going to use the value that I just computed, and it's going to be the sum of the exponentials. Kappa is 1, so there's nothing in front of these. That's just a formula that I just written, and I'm going to add 25 terms of both m and n. So overall, it's going to be 25 squared number of terms in this summation. Since this is going to take a little while to plot, I'm not going to use the manipulate command because it's going to be quite slow. So instead of, I'm just going to plot this function for several values of t, going from 0 to 0.1 second. The heat dissipation happens quite quickly, and the most interesting things happen very close to 0. So this is where I'm going to be interested in seeing what's going on there. After a little bit of waiting, you'll get this graph. So this is the temperature distribution approximated with the sum of 25 suns and 25 suns of x and 25 suns in terms of y. And after 0.01 of a second, the temperature kind of softens up and starts to flow away from the square. And then you can see how the 0 temperature ends are dissipating all of the energy away from this plate. So the formulas that we used are not really that different. The big change is the two-dimensional integration formula that I'm employing right here. That now our dot product is going to be two-dimensional because we have two dimensions x and y right here. The derivation of two-dimensional wave equation is pretty much the same. So let's go ahead and do it. The equation is slightly different now. We have utt equals some constant c squared times, let's just put uxx plus uyy here. So assume that x belongs to interval from 0 to a, and y belongs to interval from 0 to b. We can assume that this is a pinned membrane, that the sides of it are fixed. So we have that u of 0y for all values of t is the same as u of ay at all values of t, and it's the same as u at x when y is 0, and u of x at y equals b, but all of those are equal to 0. We've fixed the sides of the membrane, so we can think about it as a rectangular drum. Now, since there are two time derivatives, we need two initial conditions. So we're going to assume that u of x, y, and at t equals 0 is some kind of function of x and y, and ut of x, y at t equals 0 It's a correction to the equation above. That's some function g of xy. Given our previous experience, we're going to assume that u of x, y, and t is some kind of a summation in terms of two indices m and n of a function u, m, n, where each function u, m, n is going to be a product of x times y of y times t of t. Plug it in and see what happens. Taking all of those derivatives, we get t double prime times x times y should be equal to c squared times x double prime times y times t plus x times y double prime times t. Dividing everything, we get to t double prime over ct should be equal to x double prime over x plus y double prime over y. Again, first, I'm going to single out x. And again, I'm going to assume that there's a constant minus sigma that both of the fractions are equal to. Repeat the process, we'll get that x double prime plus sigma x should be 0, x of 0 should be 0, as well as x of a. That leads to the solution, x of x being sine of pi n x over a, and the constant sigma being pi n over a squared. Repeat it again for y, we get that y double prime plus eta y should be 0. Since the membrane is pinned, both ends of the membrane for y equals 0 and y equals b have to be at 0, and the solution that we can get for it is going to be sine of pi m y over b, and the constant eta will be pi m over b squared. This finally leads to the t equation that is almost the same as what we had before. Now it's t double prime over c squared t plus sigma plus eta should be 0, which means that t double prime plus c squared, and I'm going to plug in eta and sigma in here, pi n over a squared plus pi m over b squared times t should be 0. This is a second order equation and has exactly the same solutions as the equation we obtained for the single dimension wave equation. That is, that t should be some kind of a constant that depends on n and m times cosine of c times the square root of pi n over a squared plus pi m over b squared times t plus b that depends on n and m times sine of c times the square root of pi n over a squared plus pi m over b squared t. This means that the overall solution will be the sum as n goes from 1 to infinity, the sum as m goes from 1 to infinity, the product of all these functions. We have a n m times cosine of c times the square root of pi n over a squared plus pi m over b squared t plus b and m times sine of c times the square root with all these shenanigans repeated Now the whole thing will be multiplied by sine of pi n x over a times sine of pi m y over b. Now the last thing I'm going to do here is to figure out the coefficients a, m, n, and b and m. And that can be done with plug in t equals 0. For plug in t equals 0, we have that u of x, y at t equals 0 was fixed to be f of x, y. And that should be the sum as n goes from 1 to infinity and m goes from 1 to infinity of plug in t equals 0, and you quickly see that sine disappears. It's just a and m times cosine 0, which is 1, so it's going to be just sine of pi n x over a times sine pi my over b. And therefore each coefficient a and m will be t over a times t over b times the integral from 0 to a, integral from 0 to b of f of xy times sine of pi n x over a times sine of pi my over b dy dx. So this is how we find coefficient a. Now you can see where it goes with the coefficient b. For the b coefficient we have to use the second condition, which is ut of xy0 was g of xy, and that's the sum as n goes from 1 to infinity times the sum of m going from 1 to infinity. Now I have to differentiate this with respect to t. Now I do know that the cosine is going to differentiate into negative sine, and then when I plug in t equals 0 it's going to disappear. So it's going to be just b and m times c times the big square root of pi n over a squared plus pi m over b squared times cosine at 0, which is going to be 1, times sine of pi and x over a. These functions depend on x and y, therefore t derivative doesn't affect them. Sine of pi m y over b. You can quickly see that the coefficients b and m are going to be computed just like the coefficients a and m, with a little twist. So it's still going to be t over a times t over b times 1 over that monstrosity, c times the square root of pi n over a squared plus pi m over b squared, all under the square root, times the integral from 0 to a and then this time it's going to be the integration of g of xy times all of those signs. So here I prepared a simple problem. I'm having an interesting initial condition that it's just the same function, but now it's when I plug in x and I plug in y and then multiply them together. And this function has an interesting graph. It's sine of x, but only for a small period of it. So here I have x and y both going to the both on the integral from 0 to 3 pi, and the sine of 2x only applies when x going from pi to 3 pi over 2. It starts at 0. Then as x rises from pi to 3 pi over 2, we get the sine 2x will go from 2 pi to 3 pi. That means the sine 2x will only go through half of its cycle, and it's going to be 0 again. So when I multiply these functions, the graph that I'm going to get is I will have this function sine, both applied in terms of x and y. And it'll give me this kind of bump in the xy plane, and then the rest of this is going to be 0. So if this is the original configuration of my membrane, then I can assume that it's going to be waves kind of propagating to both sides and then being reflected from different sides of this rectangle, and we'll see what happens. So here the function f of x is given. This is the configuration, the initial configuration of the membrane. It's like it's being hit from underneath real quick. Then I'm computing coefficients a, m, n. Coefficients b are going to be 0 because the function g is 0. Integrate from 0 to 3 pi in both x and y. I get sine of pi n x over 3 pi, so pi and pi cancels out. That's why I have nx over 3 right here. T over a and t over b end up being t over 3 pi squared, so it's 4 over 9 pi. And that's how I get my coefficients a, n. There will be problems with those coefficients. You can see that when m turns 6 or n turns 6, or both of them are 6, we have 0 in the denominator. So what I'm going to do is I'm going to compute those limits, and I'm going to multiply by coefficient a, m, n. But when m and n are both 6, I'm going to use the coefficient a66. When n is 6, I'm going to be using the coefficient a6n, so am6. And when m is 6, I'm going to be using the coefficient a6n. I don't need this 1/3 because I didn't have any c squared in front of it. So you can see that the waves propagate to the sides, then they reflect. So here comes the question. We have those traveling waves phenomena, but it seems like we have the products of stationary waves sine nx and sine my. So here what I want to do is I want to demonstrate how each component, so for example the component when n is 2 and m is 4, is just a stationary wave that just oscillates up and down. So a component with both n and m being 2 is just a wave. It goes up and down. Let me make those waves a little bit more pronounced. You can see those are stationary waves. And just the summation of those waves produces this traveling wave phenomenon. Let's look at another one, n being 3 and m being 2. So what happens? Interesting waves when n and m are being 1. So the summation of these stationary waves produces this effect of a traveling wave. And we've seen that in the solution of the single-dimensional wave equation already. Here I produced a little video of those frames, and I also uploaded to YouTube, so feel free to check it out. Initially, I have a single wave, and then as the waves get reflected multiple times, it produces this kind of a mess. But it does have some mathematical beauty to it. The last thing I want to discuss is how does the wave equation change if we start talking about the circular domain. We've already seen the circular domain in the case of the Laplace equation. In the case of the wave equation, things are getting complicated very, very quickly. So the equation is going to look like utt equals c squared, and we have a Laplacian for the circular domain, durr plus 1 over r u sub r plus 1 over r squared u theta theta. We're going to assume that the solution looks like this. It's going to be the summation in terms of n and n of some building block solutions umn of r theta t, and each umn is going to be the product of a function of just r, a function of just theta, and a function of just time. I'm going to assume that the boundary is at 0, and assume that the initial condition u of r theta at t equals 0 is some function, depends on r and theta, and ut of r theta time equals 0 is some function g of r theta. We're going to assume that all of those functions are 2 pi periodic in terms of theta, and also for compatibility we would like to assume that g and f are both 0 when r is capital M. So applying separation of variables leads us to this equation. R times theta times t double prime should be equal to c squared times r double prime times theta times t plus 1 over r times r prime times theta times t plus 1 over r squared r times theta double prime times t. First I'd like to single out theta. So if I single out theta, I get this equation that r squared times t double prime over c squared t minus r double prime over r minus 1 over r prime over r. All of that should be equal to theta double prime over theta, and that has to be some constant sigma. And I'm going to use minus sigma for obvious reasons, because I want my equations to be a little bit less complicated. For theta, this means that theta double prime plus sigma times theta should be equal to 0, and that's given that the theta of 0 should be the same as theta of 2 pi. As we have seen, this leads to Fourier series solution for our theta. Theta is either constant or a combination of sine and cosine. So I'm going to call it A times cosine, and we have n theta here plus b sine of n theta, and sigma just has to be n squared. Following the same procedure that we did for the heat equation, break the rest of the equations into the equation for t and the equation for r. We're going to single out t first and then do something for r. Breaking apart the left side fraction, we get that t double prime over c squared t should be equal to minus sigma over r squared plus r double prime over r plus 1 over r times capital R prime over capital R. And given that the both sides of this equation depend on different variables, this must be another constant. This leads to two equations, one equation for t and one equation for r. And for r we have a boundary condition that r of capital M should be 0. At this point we'll have to be very careful on how we solve this equation. The solutions for t are quite obvious. It's going to be sines and cosines. Let's figure out what happens with r first. So we have an equation, and I would like to multiply by r squared. Get r squared plus r double prime plus r times r prime plus 80 times r squared, and sigma was already decided to be n squared, so it's just n squared times r. That should be 0. Let's use Mathematica to solve it. So the Mathematica gives us that it's either Bessel J or Bessel Y function. Let's plot one of those functions. And since we need two variables n and eta, I'm going to manipulate both of them. So the Bessel function is a wave-like function. If I change n, it changes the type of the Bessel function. If I change eta, it acts as a scaling coefficient. And you see that for certain parameters of eta, I can get it to be 0 at the end. So this is how we can figure out eta. It will be the coefficient that will make the Bessel function to go to 0 at the endpoint. And for each different n that come from the function theta, I will have a different type of the Bessel function playing the role. If I let eta to go a little bit higher, you can see that all of those functions will go to 0 at some point for the right eta. The Bessel y functions are not the ones that we need because they go to infinity. For all different types of the Bessel y functions, they all have a discontinuity at 0, and that's why we're not using them here. So it looks like R of R is a Bessel function that we denote as capital J of n, and here we have to use square root of eta times R. So how do we figure out the right parameter square root of theta? Well, suppose x sub m n is the root, the mth root of j sub n. Then we need square root of eta times m, because that's the radius of the disk, to be exactly that root. Therefore eta is a square of x mn over m squared, and that eta depends on m and depends on n. Thus R of R is the Bessel function of order n of x mn times R over m, and all we have to do now is to figure out the solution for the function t. The equation for t reads t double prime plus c squared eta times t equals 0, and then it has a set of solutions. It's going to be some coefficient times cosine of c times square root of eta t plus some other coefficient times sine of c times the square root of eta times t. Now, if eta depends on m and n, then t depends on m and n. And we also get theta having its own coefficients there. So when we multiply all of this together, we get a ginormous summation of things. We'll treat the case n equals 0 as a little bit of special case. So for 0, we have to add, as m goes from 1 to infinity, and n equals 0, so we use the Bessel function 0 of x m0 times r over capital M multiplied by t of t and theta of theta. So we have a sub m cosine of c times the square root of eta is just x m0 over m times t plus b sub m times sine of c times x m0 over m t. And theta was just a constant. Multiplying constant by another constant isn't going to change anything. So the next thing we had was when theta was a combination of sines and cosines. So we'll have this multiplied by sine and then this multiplied by cosine. So we're going to add another summation as n goes from 1 to infinity. We have a summation as m goes from 1 to infinity. We use the Bessel function n of x m n r over m times the function t, which is going to have coefficient a and m, times the cosine of c times x m n over capital M t plus b sub n m sine of c times x m n over m t, and all of that is multiplied by cosine function from theta, and that was just a cosine of n theta. And we're going to have exactly the same thing with the sine. So what I'm going to do is I'm going to just copy it. Now instead of coefficients a, I'm going to use coefficients alpha and m and beta, just because these coefficients should be different. Instead of cosine, I have sine. So this is absolutely ginormous expression. So to compute the coefficients a's and b's and alphas and betas, I would have to use the initial conditions. We've seen that the dot product in the xy direction was a double integral from 0 to a and from 0 to b of some function of x and xy times something else dy dx. But in polar coordinates, the dot product is different. The same double integral is going to be turning from a dy dx integral into r dr d theta. And this is something I want to stress a little bit. So here we'll be integrating against the cosine functions and the functions in terms of theta. If we look at the form of the solution that we have right here, then when I plug in t equals 0, the cosines will all turn to 1 and the sines will all disappear, so we'll be left with the Bessel functions in terms of r and the cosines and sines in terms of theta. So what we'll have to do is we'll have to integrate with respect to theta and then integrate with respect to r dr. Well, the big problem is that the dot product formulas only work if the functions that we have are orthogonal. So we do know that the sines and cosines are orthogonal, but what about the Bessel functions? Well, we know, and I'm going to leave the explanation behind the scenes, that the Bessel functions are all orthogonal to each other. The integral from 0 to m of jn of x mn over m times r times j sub n of x ln over m r times r dr is 0 if m is not the same as L. The same is true for the functions of different order. They're all going to be orthogonal to each other. Now what about the norm of j sub n? If I integrate j sub n squared of x mn over m is r times r dr, then I will get m squared over 2, the Bessel function of order n plus 1 at the root. Well, this function is not going to be 0 because here I was talking about the root of j sub n. xmn is not the root of j sub n plus 1, so this is going to be non-zero. So in order to compute all of the coefficients, what I will have to do is I will have to project onto j sub n multiplied by sine of n theta or cosine of n theta and do this weird polar integrals, and that's going to be quite a complicated thing to do. So what I'm going to do is I'm going to consider a much simpler problem where things are symmetric around the center. So I don't have a dependence on theta, I only have the dependence on r and t. So if dependence on theta disappears, then u sub theta theta disappears and my function is a product of just r and t of t, and I will only have to deal with the first expression right here. Here the capital M is 3 pi. I'm going to have to consider the j function decomposition of my initial condition only for n equals 0. Well, this is a type of this, I mean here that the u sub t of r0 is 0. I have 0 initial velocity given to my membrane. So I would compute the coefficients as 1 over the norm of the j function. So it's going to be 1 over j1 of x m0 with 2 on the top and 3 pi squared on the bottom. The integral from 0 to 3 pi of u sub r0 multiplied by j naught of x m naught r over 3 pi dr, and j1 has to be squared just as this one. And all the coefficients bm, now they're going to be 0 because the initial condition for the time derivative is 0. So let's see how it works. I have the function f of r theta given to me as that interesting function, which is just a simple dimple on the disk. So this is radially symmetric, and we don't have any dependence on theta. Nothing changes for all different angles. It's going to be the same profile for all angles. And we're right to assume that the waves that are going to be generated by this dimple are also going to be symmetric. So it's going to be, and they're going to be the same for all angles theta. So here I compute all possible zeros of the function Bessel j, and I compute the first 100 of them. Then I compute the norms of each Bessel j function that is scaled with a different scale just to give us 0 at different locations. It's 2 over m squared, so it's 2 over 3 pi squared times Bessel j of order 1 computed at each 0. So this gives me an array of norms, and then each coefficient a naught or each m is going to be computed as here I'm integrating numerically because this integral is not going to be computed in the Color Mathematica, so I'm using the numerical integration to compute the dot product of f with the Bessel function, and then I multiply it by the norm, and I do it for first 100 values of m. I'll compute the sum, the first 10 elements of it, just to save some computation time. So here what I'm doing is I'm taking the mth coefficient, this double bracket is the array indexing operation in Mathematica, very much like parentheses in MATLAB or brackets in C++ and Java. So here I'm just taking the mth coefficient multiplied by the Bessel function that's scaled with the mth root, and I multiply by the cosine function that is appropriately scaled in terms of t. Then I compute several plots of the u-sum for different values of t. So here x is r cosine theta, y is r sine theta, and z is the summation computed for radius going from 0 to 3 pi and theta going from 0 to 2 pi. So here I'm using the dynamic functionality of Mathematica that would dynamically swap those plots with different values of t, and you can see that I have a wave that goes out to the sides of this disk and then comes back and then it just oscillates back and forth. So this is my exposition to the multidimensional differential equations. This by no means is an extensive exposition to the topic, and I know that I swiped quite a lot of details under the rug. I'm doing that to give you an idea what can be done for real-world applications with the method of separation of variables. And I'd like to point out that the separation of variables is a theoretical tool, and most of the time these days the problems are a lot more complicated, and the domains are not simple rectangles or simple circles. And instead of these theoretical derivations, people much more often use numerical computations with methods such as finite differences or finite elements. And these methods are very, very powerful to give quite accurate computations and quite accurate predictions of what's going to happen to the materials and the objects that you're using in your physical environment. And although it is important to understand the theoretical in these differential equations, I would strongly encourage you to take classes that discuss the numerical methods, since those are a lot more ubiquitous in the current state of engineering. So this is where I'm going to leave you. Thank you for tuning in, and I wish you best of luck with your future studies.